Okay, next let's study a type of integration. It is a theorem. So let gamma from closed interval AB to C be of bounded variation. And suppose that f from AB to C is continuous. Okay, then there is a complex number I, whatever, I integral, such that for every epsilon greater than 0, there is a delta greater than 0 such that one P is a partition which is a equal to T0 less than T1 less than Tm, which is B, is a partition AB with the modulus of P less than delta, then absolute value of I minus the integral, the sigma k from 1 to m, f of tau k times gamma of tk minus gamma of tk minus 1 will be less than epsilon for whatever choice of points tau k and tk minus 1 less than tau k less than tk. Okay, and this I is okay. This is a end of the theorem. The theorem is done here, and we have a remark. This number I is called the integral of f with respect to gamma over AB, and is designated by this I. We write it integral from A to B f d gamma. F d gamma. If you want to use a variable, if you want to mention a variable, it's f of t d of gamma of t. F of t d of gamma of t. So this is the notation. It means the number with such a property. And second, see here, later we will see other types of integrals, and we will compare them, see the difference among those different integrals. But this one, let's first study this one. You have interval A and B. You have a complex plane. Gamma. This is gamma A, and this is gamma B, and the curve is the image of closed interval AB. And f f is also defined over the same interval AB. F is also defined over the same interval AB. So with the image whatever, we don't know the precise stuff of image, but we only know this f has a continuous image, and then we get the integral like this. Okay. Okay. 3. For example, with the most special case, let's check here. We have closed interval AB here. Well, this gamma can be arbitrary bounded variation function, right? So for example, we can map gamma AB, closed interval AB to closed interval AB by itself. Gamma. So gamma of t is just a t. T is a real number, but t is also a complex number, so it's a point of C. So this is good. So gamma tk minus gamma tk minus 1, and tau is inside AB. So if we understand this, if we try to understand this, the general case, for this special case, for the special choice of gamma, so this sigma k from 1 to m, f of tau k, tk minus 1. What is this? This is exactly a complex valued Riemann sum. Complex valued Riemann sum. Right? If you still remember what the Riemann sum is, this is complex valued Riemann sum. And we know that if function is continuous over the closed interval, then it is Riemann integrable. So that's why the I exists in this case. I always exists if f is continuous. Okay? So here, what we do, we instead map AB to itself. We map it to whatever curve. And then we're going to more or less do the same Riemann sum. It's a Riemann Stiegel sum, right? And do the sigma and take the limit. So that's like the similar construction of the Riemann sum. Okay, so now let's see the proof. Try to see the proof. F is continuous. Over AB, closed interval AB. Then F is uniformly continuous. Over the closed interval AB, right? So it's very important. It should be continuous, and also the interval should be closed, bounded and closed. Okay, then for each integer m, for each positive integer m, we can find delta 1 greater than delta 2 greater than delta 3 greater than delta m, and greater than go on, such that if s minus t, if two inputs are close enough, then the output f of s minus f of t ups value will be less than 1 over m. Okay, so this actually done step by step. You first you choose m equal to 1 because it's uniform continuity. You can find a delta 1. You can find the delta 1 such that s minus t less than delta 1 implies fs minus ft less than 1 over 1. This is the first step. Then you get m equal to 2. Then there exists delta 2 prime. But this delta 2 prime, I don't know if it is less than delta 1 or not. So here you get argument. If delta 2 prime is greater than delta 1, greater than or equal to. If it's too big, remember this delta 2 prime, you choose one. Any number smaller, less than it, will also satisfy. If delta 2 prime is greater than or equal to delta 1, we choose delta 2 equal to half of delta 1. Okay? Let's remove the prime. Just use delta 2. There exists a delta 2. If delta 2 is greater than the previous delta 1, does not satisfy this property, then we just choose half of delta 1. And half of delta 1 is still less than this delta 2, then everything works. Such that s minus t less than delta 2 implies ops value of fs minus ft is less than 1/2. And then you continue m3. Well, there exists a delta 3. And if delta 3 is greater than or equal to delta 2, we choose delta 3 is 1/2 of delta 2. And such that blah, 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 blah. So this is an inductive process, but we can always satisfy this chain of inequalities. All right, so we do have such chain of inequality. Okay, then let's back. So for each m greater than or equal to 1 integer, positive integer, let Pm be the collection of all partitions P way of AB with the norm of P less than delta m. So we do have all the satisfied partitions. Okay? Well, we know that if a partition P belongs to P2, belongs to P2, then the only requirement is that the norm is less than P2. Less than P2, we know the delta 2. But delta 2 is less than delta 1. Right? So by this condition. So we get P must belong to P1 also. So this argument can be applied to collection P1, collection P2, collection P3. So we do have the chain of collections. We have this chain of collection, right? So everyone is contained in the previous one. Okay, so each collection contains a lot of partitions. After you have partition, you can form the Riemann sum or Riemann-Stieltjes sum. So we define Fm to be the closure of the set the values set the Riemann sum. So k from 1 to n f of tau k gamma of tk minus gamma of tk minus 1. Here this partition belongs to the corresponding, the same Fm, then this is Pm, and this tau k of course is arbitrary point between tk and the tk minus 1. So first of all, even with respect to one partition, you may have a lot of different choices for tau k. So this set contains infinitely many points. And then you take the closure. Okay? So here, this tau k change, this partition also change. They both may change. Okay, now we are going to claim two facts. Fact 1 and fact 2. Fact 1 is that F contains F2, contains F3, contains so on. It is a chain of sets. And second, the diameter of Fm is less than or equal to 2 over m times the total variation of gamma. So remember this F is closed because it's a closure. Closure Fm is always closed. And second condition says diameter is less than this quantity. So the second one say it is Fm is bounded. It's bounded. So closed bounded Fm is compact. This is the result, equivalent result in the Euclidean geometry. Okay, anyway, so we need to claim them. And we're going to use these two properties to prove the theorem. So assume, now let's see how do we use those two facts to prove this. So if these two facts are proved, then we have a chain of a compact set, and the diameter will shrink to 0. Then by counter theorem, there is exactly one complex number I in the intersection of Fm. M is from 1 to infinity. So basically you take the intersection of all such Fm, then this intersection is a singleton, just contains 1 point. This result, conclusion is the conclusion of so-called counter theorem. Okay, so once we have this, we're going to show that this I satisfies the property. So here we first find the I by the counter theorem, and second we will show that I satisfies the theorem. All right, so how do we show it satisfy the theorem? So epsilon delta, so given epsilon greater than 0, we choose m is greater than epsilon 2 over epsilon times the total variation. Oh, actually, this quantity is not that important. You just pick up some large enough number. We use this number, a coefficient, just to make the final stuff better. Okay. Okay, so when we have this one, then what? Then you just switch m and epsilon. Then epsilon is greater than 2 over m times the total variation of gamma. And this one is greater than or equal to the diameter of Fm. It's greater than or equal to the diameter of Fm. Right? So the complex number, this number is in the intersection of them. What does it mean? It means I belongs to this m. I belongs to this m. I belongs to this m. For whatever point, any point P in this, the distance P and I is less than or equal to the diameter of Fm, right? This is an element in the Fm. Then for any other point, the difference or the distance is going to be the less than or equal to the diameter. Diameter is the supremum of all these distances. And this diameter is less than epsilon, right? So we have Fm is a subset of the ball centered at I. This is fixed. Every point will be close to it with epsilon radius. With epsilon. Right? So what does this mean? This means let delta be delta m. Delta be delta m. Then whenever for any partition P with the norm of P less than delta, which is delta m, then this is a collection inside the PM. Then you can compute Fm. Then we have sigma k from 1 to n f of tau k gamma t k minus gamma t k minus 1. Remember where it is? This one. This is inside Fm. This element is inside Fm, so it's inside this ball. So the difference will be less than epsilon. So this is the center, this is the arbitrary point inside the disk. All right, so you can see that those two facts will help us to find I, and then this I will satisfy the condition. This is labeled as a formula 1.6 in the textbook. So our job is to verify those two facts. Our job is to verify those two facts. Okay, now we show the two claims. Claim 1. Claim 1, remember P1 contains P2, contains P3, and so on. Hence, F1 contains F2, contains F3, contains F4, so, right? Because you just have the inclusion based on the inclusion of PM. The tau k is always tau k. It always satisfies this condition. Right? Let's see. Yeah, you can see it. So the first claim is trivial. Now let's see the second claim. Why the diameter of Fm is less than m over 2 times the total variation. Okay. we have the partition, and we have this one. We have where it is, this one, right? This is an arbitrary point inside Fm. Arbitrary point inside Fm. So let P be A equal to T0 less than T1 less than Tn equal to B, be a partition. And let S of P be f of tau k gamma tk minus gamma tk minus 1, k from 1 to n, where tau k is any point in the closed interval tk minus 1 and tk, arbitrary point. Okay, assume this partition P belongs to the PM, which means the, what's that? Which means the norm of the partition is less than delta. In other words, Fs minus Ft is less than 1 over for S minus T less than delta. All right, so let's copy them here. We will use them in the proof. Okay, so remember we are going to do subtraction of two such quantities. So first, we assume that P union a point, let's not use PT, equal to Q. We first just insert a point to the partition, then you create a refinement and you call that second partition Q. You can call this second partition Q. And we show the S of P minus S of Q modulus is less than 1 over m times the total variation of gamma. We're going to show this. Okay, how do we show it? PT, right? So let the point is between TP minus 1 and TP, between them. And this is A, this is B. It's a TP minus 1 and TP. Originally, you choose tau P, tau P. But once you insert a point PT, you got two subintervals. You have two subintervals. Then for those two subintervals, you choose sigma. Here you choose sigma prime. Okay, whatever sigma prime are any number from the chosen intervals. All right, then let's check. SQ is sigma F sigma K gamma TK minus gamma TK minus 1. If this K is not P. If it's not inside this interval, you just randomly pick up them. And if it's left interval, this one, you're going to have F of sigma and gamma of, you insert this point, gamma of the point minus gamma of TP minus 1, and plus F of sigma here prime, and the gamma of TP minus gamma of point. Right? This is SQ. And remember, we choose this P partition of P with this such property. So all the Tk minus Tk minus 1 is always less than delta M, strictly less than delta M. So if you select 2 points from one interval, then the distance will be less than delta M. So what we have this tau minus sigma less than delta M implies f tau minus f sigma less than 1 over M. Remember this, okay? Okay, now let's try to do subtraction. We're going to do subtraction as P as Q. Right, well, it's going to be long, but it's not that bad. So you see here, if it's not this interval, you get the difference of f tau k minus f sigma k and gamma tk minus gamma tk minus 1 when it is not this interval. And when it is the left interval and it is the right interval, then what we have? We have the for the P, then it is, you just get tau P. So it's f tau P gamma Tp minus gamma Tp minus 1. This is for SP. SQ is here. Just do subtraction, right? Remember, we do subtraction. Minus f sigma gamma point minus gamma Tp minus 1 and minus f sigma prime gamma Tp minus gamma point ups value. And right, so just this one, this sum is from the SQ. I remember this gamma Tp minus gamma Tp minus 1 can be written as a gamma Tp minus gamma point plus gamma point minus gamma Tp minus 1, right? Of course, we can insert some number. That's our favorite trick, correct? So apply triangle inequality and also apply this trick. We'll have sigma k less not equal to P ups value f tau k minus f sigma k, and oops, this is a gamma tk minus gamma tk minus 1 triangle inequality. And here we put this one and we distribute f tau p to this sum. So it is plus f tau p minus f sigma ups value and gamma tp, no, tp minus gamma pt, gamma point. It's a second one. And plus f tau p minus f sigma, then it is gamma point minus gamma tp minus 1. Right? Just consider it as a two sample point. And also this yes. Okay, so now let's see. Tau k minus sigma k ups value is less than tk minus 1, less than delta m. And then this Tp minus Pt less than delta m. pt minus tp minus 1 less than delta m. They all less than delta m, then by the condition of uniform continuity, so we have less than or equal to, this one is less than 1 over m. Sigma p is not equal to k, and this is a partition of value of gamma tk minus gamma tk minus 1. Here, this one is less than m, so it's factor out m. So it's a gamma tp minus gamma point. This one is less than m, 1 over m, they're all 1 over m. Gamma pt minus gamma tp minus 1. And this one, if you consider it, it's exactly the variation of gamma with respect to p union pt. So it's a variation of a gamma with respect to q. But the variation of gamma with respect to q, remember gamma is of bounded variation, so it's less than or equal to 1 over m, the total variation. Okay? So if you join one point to a partition to form another partition Q, second partition Q, and then you measure the distance between SP and SQ, it is less than 1 over m. And if you join more, actually what you do is that you just pick up more such interval and divide it into 2 parts, and the only difference is that this part you are going to write a lot of pairs, not just one pair. That's not easy to write, and I mean that's easy to understand, but it's too long to write. So we assume we only demonstrate the case when we join one point. We will say if p the other one. If P is containing Q, Q is a refinement of P. Similarly, we can show that the SP minus SQ is less than 1 over m, the total variation of gamma. Okay, similarly just means here we will have several pairs instead of just one pair. Okay, so that's the proof for the special case if one is a subset, one partition is a subset of the other partition. Now what happens if P, Q are 2 elements in PM? PQ are just random 2 elements in PM. Then P is not a refinement of Q, Q is not a refinement of P. Then what's going on? We define R to be P union Q. We create the union of 2 partitions. If we create a union of 2 partitions, then P is containing R and Q is also containing R. Right? So we get the refinement. So the S of P minus S of Q becomes S minus P minus SP minus SR plus SR minus SQ. And this is a less than or equal to triangle inequality. SP minus SR plus SR minus SQ. And these 2 partitions has a relation that one is a refinement of the other one. So we can apply what we just proved. And this one is less than 1 over m total variation of gamma. This one is also less than 1 over m total variation. So add them together is 2 over m times the total variation of gamma. So we finish the proof of the second part. The second claim. then we totally finish the proof of the theorem. A theorem is a very interesting and clever proof, and I really suggest you to review the proof and see what property you use and how we go through it. Okay? All right. Good. After we got this definition of integration, we can list a simple proposition 1.7. So let f and g be continuous functions. On the closed interval AB. And let gamma and sigma be functions of bounded variation on AB, then for any scalars, just numbers, any scalars alpha and beta, we have two linearity. The first linearity is about a function. So the integral from a to b, alpha f plus beta g d gamma is equal to alpha integral a to b f d gamma plus beta integral a to b g d gamma. That's a first linearity. It's a linear about the function. And the second linearity, the integral from a to b f d of alpha gamma plus beta sigma. It is equal to alpha integral a to b f d gamma plus beta integral a to b f d sigma. So the proof will be almost similar to the proof in the calculus. So there's no tricky part. And another simple proposition is that if we have bounded variation function, we can integrate over the whole interval, or we can integrate step by step and add them together. Okay, so let gamma from A, B to C be of bounded variation, and let f from A, B to C be continuous. And then we can cut this domain into several pieces. If A is equal to T0 less than T1, it's like a partition. Tn equal to B, but this partition is not in the definition of integration. It's actually the additivity of the domains. The integral from A to B f d gamma is a sigma k from 1 to n integral tk minus 1 tk f d gamma. Okay, you just integrate piece by piece and then add them. Okay, so let me see. Well, let's stop this lecture at this place. In the next place, we're going to show another property or the computational method about the evaluation of the integral. But so far, in this lecture, what we have done, we define a integration, and we show the existence of integration with the total bounded variation function and with the continuous functions. Okay, and then we list the similar properties of integrations. And next, we're going to have one method about a special type of evaluation of a special type of integration. All right? Okay, thank you very much. We will continue in the next lecture, and this lecture is done. Thanks.